Groundwater Relief provides hydrogeological expertise and technical advice to the humanitarian and development sectors. And we do this through a global membership of over 400 groundwater experts. This video on drilling supervision has been developed as a reference for people working in these sectors on water supply projects. Competent drilling supervision provides not only a good record of the subsurface, but also leads to well-designed and engineered groundwater sources, providing communities with long-lasting, efficient water supplies. Groundwater Relief is delighted to introduce Professor Richard Carter, a hydrogeologist who's been working, researching and teaching on rural water supply for over 40 years. Richard will be taking us through the basics of drilling supervision with a focus on drilling in unconsolidated sediments.
The supervisor is the representative of the client. He or she may be from the government, from the private sector, or from a non-government organisation. The drilling supervisor will ideally be a hydrogeologist. They should be competent to make and to implement decisions during the drilling and the borehole completion process. They need to develop a good rapport with the driller while always maintaining their own independence and integrity. The supervisor is responsible, together with the driller, for completing a successful well, if the hydrogeology can allow. On this site, we're concentrating on drilling supervision in unconsolidated formations, where the driller uses a mud flush to remove cuttings from the hole. In much of the world, the ground conditions consist of hard rock, where drilling is conducted using the down-the-hole hammer method of drilling, which uses an air flush. This method makes it easier to detect water strikes. When encountering water strikes, yields, water quality and rest water levels should be measured before continuing drilling. Drilling works are framed around a contract between the client and the driller. The drilling contract includes a specification setting out the total depth, the diameters of the drilling materials, and the details of all annular backfill materials. Successful drilling works are highly dependent on the experience of the drilling contractor. The supervisor must recognise this experience, but also be aware of any gaps in the driller's knowledge or expertise. Together, they should identify the key objectives of the drilling programme before commencing the works, referring to the drilling contract as they do so. The supervisor is responsible for any decisions to change the design taken in light of the ground conditions, and is therefore directing as well as supervising the contractor. Any change needs to be discussed, and this conversation should be recorded for future reference. The supervisor must always know how deep the drilling has progressed and all aspects of relevance to the well completion. They must keep records of the geology, the lithology, depths of water strikes, penetration rates, well consumables installed, and all events such as rig breakdowns or loss of circulation. And it's essential that a note is taken of the time each drill rod is changed in order to keep track of progress. The penetration rate can help support geological interpretation. The supervisor must maintain good communication with the driller at all times, because the drilling contractor will often be able to provide additional information that the supervisor isn't able to determine. For example, a vibration indicating encountering hard rock, or a water strike indicated by a change in the drilling mud viscosity. The supervisor must take regular and frequent samples of the drilled formation. Sample collection will vary depending on the geology and on the drilling method. On this site, we're drilling into sedimentary formations using mud rotary and cable percussion. These each have implications for how geology can be logged. In mud rotary drilling, samples are collected from the upflowing drilling muds. Samples are normally collected from the trench that takes the mud from the borehole to the mud pits. With cable percussion, samples are often less damaged by the drilling process. Other drilling techniques lead to variation in the nature of the sample. Samples should be stored and labelled so that they can be examined later. The sample is examined visually and by feel. Sands feel gritty between the fingers. Silts feel soapy. Clays are malleable and able to be rolled. Samples are described by their texture, colour and grain size. Recording grain size is very important in water well drilling in unconsolidated sediments, as this has a key bearing on the well design, with the coarsest materials likely to be screened. It's common to carry out a sieve analysis on samples later to obtain further information about the geology and the aquifer system. Drilling muds carry the broken material from the borehole, depositing the cuttings in a mud pit before the mud is recirculated down the hole. The hydrostatic pressure of the mud also acts to prevent collapse of the hole. The mud pits are commonly designed in two parts, one for settling and one where the pump is placed to recirculate the muds back down the hole. Mud pits should have a total volume of 1.5 to 3 times the total volume of the borehole. It's important to maintain mud viscosity which is sufficient to carry the cuttings and support the wall of the hole from collapse. Mud viscosity is monitored using a marsh funnel. When drilling with a liquid to flush the cuttings out of the borehole, the driller can use plain water, but that has a limited ability to carry cuttings out of the hole and a much more limited ability to support the wall of the hole from collapse. And so often the driller will add an additional chemical to the water to increase its viscosity and produce a material which has sufficient viscosity to carry particles out of the hole, but not so viscous that they won't drop out in the mud pit. Because if they continue to circulate through the mud pit and then back down the borehole, we're just circulating the cuttings round and round. So the driller and the drilling supervisor will be wanting to monitor the mud viscosity. And that's done using a marsh funnel. The way a marsh funnel works is that the funnel is filled up. I'm just going to demonstrate this with plain water first of all. The funnel is filled up to a mark on the inside, and then it's timed as it flows through the funnel. And plain water takes about 26 seconds to flow through the marsh funnel. That's in contrast to a viscous drill mud, which is particularly designed to carry out the important functions of carrying cuttings, dropping cuttings, and supporting the wall of the hole. And when that material is put into the marsh funnel, you can see that it's much more viscous, and it will take a lot longer. And a typical drill mud will take maybe 40 seconds to flow through the funnel, and that's a good way of monitoring the viscosity. In some cases, a driller might keep a container full of much more viscous material in case circulation of mud is lost during drilling, and he then needs to place some more viscous material to line the wall of the hole and prevent circulation loss. Drilling mud velocity can be calculated using a bucket and a stopwatch to determine mud flow rate, and then dividing this by the area of the annulus. uphole velocity should range from about 15 to 30 meters per minute. If artesian conditions or running sand are encountered, it might be necessary to increase the density of the mud using additives. Once drilling has reached the total depth specified in the drilling contract, or perhaps a greater depth if that's agreed between the supervisor and the driller, final decisions must be made about the well completion.